Hello everyone, I am Dr. Siddeshwar Chopra and we'll continue with the wave mechanics. Today we'll be learning a very important experiment which is called Davisson Germer experiment. Let's start. Davisson Germer experiment demonstrates wave nature of the electrons, which confirmed the earlier hypothesis given by Debroglie, the Debroglie hypothesis. In 1927, Clinton J. Davisson and Lester H. Germer shot electrons onto a nickel crystal. The experiment was performed inside a vacuum chamber for the purpose of measuring the energies of electrons scattered from the nickel target. Electrons from a heated filament are accelerated by a voltage and allowed to strike the nickel crystal surface, which could be rotated to observe the angular dependence of the scattered electrons. So here is the setup diagram of the Davisson Germer experiment, wherein you see an electron detector, which is also called as Faraday's cage, is rotated to capture the scattered electrons at different angles. It was observed that at certain angles, a peak in the intensity of the scattered electron beam occurs. This peak demonstrates the wave behavior of electrons, which could further be interpreted by Bragg's law of X-ray diffraction to calculate the values for the lattice spacing in the nickel crystal. We see the diagram here. This is the electron gun, and here you have Faraday's cage to observe the electrons here, and that is how we continue. And let me go ahead. Hence, when the de Broglie wavelength was inserted into the Bragg's condition, the observed diffraction pattern was predicted, thereby experimentally confirming the de Broglie hypothesis for electrons. So this is your Bragg's law of X-ray diffraction, which is 2d sine theta equal to n lambda. Theta is the angle between the beam and the Bragg's plane, and d is your interplanar spacing, and n is any integer. The experimental result of the Davisson Germer experiment showed several peaks of scattered electron intensity with increasing accelerating voltages. This data is further collected at a fixed scattering angle. It was found that an accelerating voltage of 54 volts gave a definite peak at a scattering angle of 50 degrees. Now angle theta in the Bragg's law corresponding to 50 degrees scattering angle is 65 degrees. How does it come? That is your 180 degree minus 50 degree divided by 2. And the nickel lattice spacing is 0.92 angstrom. Hence, using Bragg's law, lambda comes out to be, by substituting the values of lattice spacing and the theta, we get 2 times 0.92 angstrom into sine of 65 degrees comes out to be 1.67 angstrom. You see here, this is the specific experimental conditions at which they found the maximum peak intensity, and hence it was confirmed that this peak is an observation or the result due to the electron diffraction, and hereby electrons were designated as matter waves. So you see here in the next slide, now for the confirmation of the de Broglie hypothesis, the wavelength was also calculated by applying the de Broglie relation, which is lambda is equal to 12.27 by root of V angstrom. Putting the values of H, M, E and V, which is specific in this case 54 volts, into the above equation, we get lambda to be equal to 1.67 angstrom. The above wavelength value calculated using de Broglie hypothesis is an excellent agreement with the one found using Bragg's law. Thus, the beam of electrons accelerated by a potential difference of 54 volts behaves like waves of wavelength 1.67 angstrom. Here in the diagram, we can see the intensity of the peak observed in the experiment was maximum for 54 volts, and then it kept on decreasing. The plot is between intensity and root of accelerating voltages. So that is all for the Davisson Germer experiment. Thank you everyone.